Hello, this is Daniel Ritchie, the developer of Howler Digital Painter. I'm not going to be talking about that today, though. I'm going to be talking again about Lightwave and some ideas that are kind of fun to experiment with. Today I'm going to be talking about path tracing in Lightwave. And yes, there's a node they call path tracing and a tool they call the path tracing tool. But that's not what we're going to be talking about. We're going to talk about path tracing in the rendering sense, which is a form of ray tracing. Um, the idea behind path tracing is to get rid of all the stuff that has accumulated over the years, all the tricks and approximations of 3D lighting, and replace them with a very simple, if a little bit brute force algorithm that doesn't approximate the lighting or the rendering algorithm, but it more or less emulates the real world uh, lighting. To put it in a simple way, path tracing is based on the assumption that all lighting on a spot, or more specifically, all the surface lighting of a spot is based on the sum of all light that hits that spot. So basically, if light hits a spot, that's the color of the spot. There's no more fancy trickery. There's no shadow maps. There's no ray trace shadows. There's no Fong or there's none of the blends or the Lamberts or any of that crazy stuff. There's no ambient occlusion. There's no global illumination. It's all part of one unified lighting algorithm or rendering algorithm. And basically, to do this, we start with a very simple lighting algorithm, which is based on a surface normal. Let me go into Lightwave. This will be a lot easier to explain once I go into Lightwave. I'll just show you a few demonstrations. Here's as you can see, we've rendered a few test shots. These surfaces all have different types of parameters on them. Some are more reflective and some are less reflective. For example, this one in the back has a very diffused lighting or diffuse, and these ones on the sides are both semi-reflective and semi-diffuse. This donut in the middle is somewhat luminous, and this dodecahedron on the top is very bright, and that's basically where all the light in the scene is coming from. That's another aspect of path tracing. There is no distinction between light objects and geometry. Everything in a path trace scene is geometry. Lights are geometry, all that. So basically, we're going to go ahead and present a way to do this in Lightwave, both using nodes, and then we might have a little surprise at the end. So let's go ahead and get started. Here's a couple more. As you can see, this not only takes care of global illumination, it also does let's see, it does sort of ambient occlusion like effect. It does this lighting based on the luminance coming from this donut and this dodecahedron at the top. It does reflectivity. It does quite a bit. It even does caustics. If you look at this water, you see reflections of these water ripples on this object, and it's not something we programmed in. It's all part of the lighting model. We get it for free. Well, we get it not so much for free. It's sort of a brute force approach, but we do get it, and it comes as part of the model. It's not something we had to program in there. You also see that on these surfaces there's reflections, soft reflections of the other objects in the scenes. You see this blue light reflected from the top of this scene. You see these little bits of reflections and other things coming from the other objects. It's all part of the algorithm. So I'll go ahead and get into Lightwave, and I have a basic scene I've set up with some primitive objects. And I'm going to go ahead and go into Nodal to demonstrate some of the things we've done here. So going into the surface editor, and I'll pick our first ball object. Go to edit nodes, and as you can see, we've set up a very simple compound node here that has a few basic items that we can plug into it. The world spot, the surface normal. There's an item info here that contains our camera, camera world position. There's a scalar. This is let's see, this is plugged into the reflectiveness. There's a color, which is plugged into the color property there, and then there's a luminous thing plugged in there. So those are all the attributes available to this surface: color, luminosity, reflectivity, and the rest are there to basically provide information to the surface of the shape, and the shape of the surface and the position of the camera. And as you can see, the one output is diffuse shading, which goes into the diffuse shading output or input, or I'm not sure how you want to think about that, but it goes out to the output of diffuse shading on the that thing there. All right, so let's take a look at our path tracing compound node. We've gone inside of it now, and then you see a lot of stuff going on here, a lot of noodle code going on. There's two ways of looking at the node editor. One is to think of it as sort of a non-linear version of the layer panel, of the layer mixing on the regular surface panel, and then other people are going to think of it as sort of a visual programming metaphor. If you've ever used Amiga Vision or something like Bars and Pipes or one of those, you might think those were maybe the prototypes of what we have now in the nodal editor. It's sort of a visual programming language in a fashion. In fact, the only thing really missing from a programming standpoint would be things like looping and maybe some of the more complex data management type of things, arrays and that kind of thing. But going back to what we were talking about, path tracing, the first thing we had to do was create a random normal. A normal is basically a vector facing outward from the surface of your object, or the face of your object, or the face of a polygon. When I say a normal or a vector, I mean it's just a line pointing out in a direction. Nothing super complicated about it. It's just a way of telling the direction the face is pointing. So when we create a random normal, we do this because we want all of the light in our scene. We want to be able to sample light from many different places in our scene, so we want to randomly shoot out all these rays, all these ray trace rays in different directions from the face of our model. And the first thing we had to do was create that random normal. The second thing we have to do is, since that's incredibly random, it might be facing inside the object, for example. We interpolate this with the existing normal, or the existing vector facing out from the face. Let's see, interpolating it by like 0.49, not quite 0.5, because that might land directly on the face, and you'd have a normal with no magnitude, basically meaning it wouldn't go anywhere. So it's slightly off from 0.5. But we're basically, when I say interpolating, I just mean we're averaging or blending between one and the other by a specific amount. 0.5 would be like right in the middle. So that's not anything real complicated. There's the algorithm that does that. There's a clamp and a subtract, a multiply and add, and some other things. Normalize basically sets that normal, the magnitude back to 1 in case it's changed. As we were in the process of adding that random value to it, it might be more or less than a magnitude of 1. Magnitude basically means the length of the line. Alright, so going back out to our compound node, there is also here, there is a reflect normal, and this is how we do ray tracing. We basically get the position of the camera in space. We subtract that from the world spot, which is the point on the surface that we're shading, and that basically gives us a vector facing from our camera to the spot, or maybe vice versa, facing from the spot to the camera. We normalize that. That makes it a length of 1. And then we pass it into this reflect normal routine so that we're reflecting the ray from our camera against the surface normal, and it shoots off in the opposite direction basically of the surface normal, or the opposite angle as the angle between our camera and the surface normal. That's a little complex sounding, but I'll be probably making a library of all these nodes and posting them shortly. So if you're not getting any of this, don't worry, it'll all be in there, and not to worry anyways. And I'll probably also post this compound node that does the the path tracing, so you won't have to know every last detail about this. A few other things we've done: we've taken this color and we multiplied the result of all the shading that we got by the color, so we have a way of controlling the color of our surface. And we also added a luminosity, and we added that to the final result, so we not only get the color of our surface, but we can add some luminosity to it as well. And then we go back to our output, and that is basically the entirety of our path tracer. It's basically taking a random normal, shooting a ray off in any direction. Well, not really in any direction, but in any direction that's within the hemisphere of the face of that the polygon that spot is sitting on, meaning it won't go back inside the object, but it'll always shoot outside of the object, but in a random direction, as long as it doesn't intersect the object itself. And basically that's what path tracing is. It's sampling random spots in space, and wherever that light falls, whatever color is returned by that ray traced path is averaged into our surface, and that's it. Nothing complex about it. Now, going to a few other little things here. Our random normal was actually created by turbulent noise. I had tried originally to create this from a random number, but it ended up being a lot of hassle. And then I realized basically turbulent noise is a random number. It's based on random numbers, so it works perfectly. I just output the bump from that into a vector and plug that into our result, and that gives us a perfectly good random vector. Nothing really complex about it. So let me leave here now. That is basically it. Let me try to turn on VPR shading, and as you see, that in very rough form is our path tracing lighting model. And from that little bit of code, or that little bit of node, we get all this complex lighting. We get drop shadows. I'll even go into the render globals here, and I'll show you to prove it. We have ray trace shadows turned off. We have reflections turned off. We have refraction turned off. We have occlusion and all this stuff turned off. We have shadow maps turned off. We have global illumination turned off. All this is coming just from ray tracing. Say this little spot right here, maybe where my pointer is shooting off a ray up here. It hits this light up here, and it knows, well, this will have some of that color in it, or it might also shoot over here and it'll have just a little bit of that color in it. And basically, well, it's very grainy right now, but how we get around that is we just use a whole lot of samples. Going back into rendering camera, I have minimum samples set to 120. In path tracing, they say about 200 samples is about the right amount. I'm using a little bit less. I don't mind being a little bit grainy, and I'm trying to save some time. So that is all there is to the idea behind path tracing. But it produces, by its nature, it produces all of the results you normally get through a large number of approximations. As you can see, there's a specular spot on here that comes naturally instead of using some complex math formula. As you can see here, there are reflections in here. It's reflecting the colors from this. It's reflecting these greens in here from that. There's luminosity that's hitting all these other surfaces. There's a drop shadow under it. There's also some luminosity hitting this surface underneath it. There are soft shadows underneath all these objects. We're getting a soft shadow because this is a very large object. If we had reduced the size of this object, we'd get much sharper shadows here, although the noise would be a lot more intense because fewer rays would actually hit that, so you'd have to use more sampling to take care of that. It is actually hard to get a hard edge shadow in a path tracer, but that's you know, a matter of how much sampling you're willing to use. So if you've been paying attention, and I don't know why you would be, but you probably thought to yourself, well, aren't you basically ray tracing a bumpy surface? And you kind of hit yourself in the head. Yeah, I guess I am. So let's try something as an experiment, and won't this be a hoot if this works? Let's see. Say we go into Lightwave, another instance we have loaded. And as you can see, let me go back into render globals. We have, same as before, radiosity turned off, on all these other things turned off. Ray trace reflection is the only thing that's turned on in this case. Shadows and all that stuff is turned off. Now let's go to our surface editor. And I'll go to, let's see, not the toroid, let's do the toroid. Go to that surface. Look, no nodes. We've done an exact path tracer, or, well, a reasonable path tracer in Lightwave with no nodes. How did we do that? Well, remember how we created that random normal that shot rays in every direction? Well, what if we just made a bumpy texture and ray traced it? It would be the exact same thing. We've created a texture with a very small size, a 10 UM. I don't even know what a UM is. It's very small, though, I think. It creates a randomly bumpy surface, but it's so small that you don't perceive any kind of shape from it. You just get a diffused lighting effect. And the only other thing we did was we added reflection. We set it to 100% right there. If you look here, diffuse is turned all the way off. And in the case of this donut, we have luminosity turned up. In fact, I'll bump it up a little bit more, and you can see our donut gets very shiny here. And it starts reflecting light on these other objects. And, well, lo and behold, we've created a path tracer in Lightwave with no code. It's basically Lightwave already is a path tracer. Who knew? Alright, so where's path tracing come in useful? Well, it's a physically accurate lighting model, so it can produce very realistic results. I believe Blender's Cycles is a path tracer. Not sure if F Prime is, I forget. I don't think I've ever actually looked into that, but I think F Prime might be. And there's some other famous path tracers out there as well. But the idea is to produce a physically accurate lighting model using a very simplified programming approach, which unifies all these crazy approaches, all these crazy things like global illumination and soft shadows and ambient occlusion and let's see. I think, like I said, we got some caustics in there in that one scene we had, and all kinds of crazy stuff. And it's just a result of sending one or a number of rays out from a point and accumulating the values that ray finds. And that's about all there is to it. Hope this has been educational. I believe I'll be able to post the nodes because some of that stuff might be useful. There's some good stuff in there. The reflecting around a normal was kind of cool, and the linear interpolating node was pretty neat. Hope you enjoyed watching. Hope you enjoyed learning how to create a path tracer in Lightwave. It's maybe academic, but maybe you'll find a use for it. And talk to you later. Thanks for watching.